I'm going to introduce Perry Krug, who is our Senior Solutions Architect here at Couchbase.
Thank you, Ali. Thank you, everybody. A pleasure to be here today. Thank you all for joining us at this conference. This session, I'm going to focus on introducing some of the considerations and practices of deploying and running Couchbase in production. So we're going to start with deployment itself, a little bit of hardware and cloud considerations, a bit of setup on the client server side, and then spend most of the time talking about the various types of maintenance that either that we're doing ourselves or that you want to be handling or tuning. So from a deployment perspective, this is the kind of environment that we're talking about, where a number of application users, typically from mobile devices or browsers, are coming into your data center, your application, connecting in through a load balancer, getting fanned out to the application servers that are then talking to the Couchbase nodes. And looking at that layer a little bit more deeply, the application server, the application is going to have a Couchbase client library. We'll talk about that a little bit more in a minute. That makes a bootstrapping connection to one of the cluster nodes, gets a list of topology, gets a list of the nodes, the list of the shards that are laid out within the cluster, and then those blue lines is the indication of traffic being sent directly to the nodes for those requests. The black being the internode communication, not showing here the cross data center side of things. One of the interesting parts of this environment, I think, is that there's nothing else in the environment. There's no other piece of the architecture that you need to set up. There are no name nodes, there are no proxy nodes, there are no cache layers separate from persistence layers. And so when customers ask, what is a deployment architecture, it really is this simple. It's set your application up to talk to the Couchbase nodes, and the nodes will, and that link will take care of everything else. So you don't have to worry about setting up all these different components and which ones do I scale and which ones are my bottleneck. The Couchbase client libraries are doing all of the load balancing for us. Okay, so for hardware, when you're first getting started, Couchbase is designed for commodity hardware. Now, commodity means different things to different people. A 128 gig SSD-based 32-core 3U system might be commodity for some people. A M2 extra large Amazon instance is commodity for others. So whatever your definition of commodity is, Couchbase should be able to run on that. We don't have strict requirements for very beefy disk systems or CPU cores. Certainly we make better use of more resources, but unlike relational databases especially, you shouldn't be looking at specialized hardware for Couchbase. And certainly focusing more on scaling out rather than scaling up, that being the idea of adding more nodes rather than incrementally increasing the capacity of each one. We do test and deploy in EC2. We do a number of our own testing. About 50% of our customers are running very successfully inside of EC2. While physical hardware is going to provide the best performance you can get, there's no reason that you shouldn't be able to use virtualized and cloud instances. It just means that you have to take certain things into consideration. Typically, you're going to end up using more nodes of less power, either virtualized or cloud, than you would otherwise with physical hardware. Especially with VMs, you want to be careful not to have more than one Couchbase node running on a physical host. That leads to a failure of that host is going to take down two or more Couchbase nodes, effectively breaking our replication and clustering capability. And also be very careful about overcommitting at the VM layer at the physical host. It's very typical for web application servers and those that don't need dedicated resources to be overloaded in terms of RAM and CPU capacity of an underlying system. Couchbase really is going to be RAM intensive. It's going to use and expect the RAM that it is being given. And if that RAM has actually been swapped out or is being shared with another system, we're not able to perform at the ways we expect to. And to some degree the same with CPU. Did you have a question?
Just you say one Couchbase VM per
So the question was around having more than one VM, more than one virtual machine on a physical host if you have the ESX high availability built in. To be honest, I'm not as familiar with that as I'd really like to be. My initial answer would be no, but if you are comfortable that a physical machine going down is not going to take down those VMs, then yes. And just as some basic rules of thumb, we recommend 3 or more nodes. While 2 nodes gives you replication, any failure of one node, any need to upgrade a node, any need to scale beyond that is either putting a single point of failure or putting all the load on just those 2. And so we recommend, regardless of your other sizing considerations, and I'll talk about sizing much more in my session after this one, 3 nodes is going to be your best high availability and resiliency in production. At least 4 gigabytes of RAM, and then in many cases much more than that, depending on the data that you're storing. 4 CPU cores, and adding on top of that, depending on the functionality that you're making use of. And I always recommend using local storage. The question comes up: can we use a SAN? Can we back it with a NAS? And while those can provide performance and they can be highly available, you're now bottlenecking and breaking some of the distributed nature of Couchbase. So much of our benefit comes from having a completely shared nothing system, that putting all of that on a single disk system, even if it's multiple disks, could be highly available. It's a single bottleneck system, and any problem there, whether it be the network or the drives themselves, is now going to affect all of the Couchbase nodes connected to it. Whereas if everything is using its own local storage, any problem at one of those layers is going to be isolated to just that node. When we talk about deploying, yes, question? So when you start talking, so storage is not just for the performance of Couchbase, and you're right. Most of what we do, most of our performance comes out of RAM, but we do need to be able to persist data to disk. We do need to be able to persist some of our own checkpointing and sequence numbers to disk. During a rebalance, you're going to be using the disk to read and write some of the data. So it's not just about the performance that your application is getting. It's really about the functionality of the whole system. And if we start talking about cross data center and views, those are going to use the disk I/O a lot more. A lot of our statistics gathering uses disk I/O. So it's not just about the data cached in RAM. So the question was about the difference between Memcached buckets and Couchbase buckets. Memcached buckets are just the off-the-shelf Memcached. It's using literally that same open source code and project, so you don't have replication, you don't have rebalancing, you don't have any persistence or the views across data center replication. So no, you don't get all of the redundancy and the resiliency that you get with the Couchbase side of things. So when we start talking about deploying in Amazon, there are some just general, Amazon and cloud, there are some general considerations to take into account. In many cases, it's not required, but in many cases, using an EIP or a host name can provide easier ways of connecting to, especially as IP addresses may be changing as nodes reboot underneath. In Amazon, using multiple EBS drives gives you better performance for that persistence layer, and also mitigates the slowdowns that occasionally happen to EBS as part of Amazon's environment. When you're talking about cross data center replication, you need to use a host name across regions, and this has to do with how those IP addresses are resolved. And at the moment, we have some documentation and recommend using Amazon's built-in VPN between regions if you want that data encrypted. And as with virtual environments, cloud in general, you're most likely going to lean towards more nodes of lesser capacity than you would otherwise with physical hardware. Continuing along with Amazon, your disk choice is an important one. The ephemeral drives are usually okay. They're not as reliable, obviously, and in many cases, our customers put their data on an EBS drive and use the ephemeral drive for indexes and views, and that's a decision that you can trade off and make. If you're going to use your ephemeral drive, you still have the ability to take backups of that data, so it's not that it's completely lost if a node goes down. The SSD instances are very nice and powerful. They're also very expensive. We have one customer in Israel about to deploy with many hundreds of SSD instances, and they're using those for the performance that they wouldn't otherwise be unable to get by being in Amazon on just EBS or ephemeral drives. That last point, deploying across availability zones, at the moment we don't have the intelligence built in to actually segregate data between availability zones. That's something we're adding hopefully by the end of this year. But even still, separating your nodes across availability zones means that the failure of one zone is not going to take out your entire Couchbase cluster. It may take out an active and a replica, and so you'll have to do some recovery from that. But at the odd chance of a whole zone going out, you don't want your entire database to be offline. Okay, so when you're getting ready to set up and deploy Couchbase, the server side is almost always and usually very simple. There are very few things that you need to do. There aren't many configuration parameters to take into account. We'll start to look at and talk about some of the more common tuning and tweaking, but I always recommend going with the default installation, seeing whether that meets your needs or not, and then adjusting from there, rather than taking the MySQL model of 100 or 200 different configuration items that no one even really knows what they do anymore, and having to tune each one of them. Again, using 3 or more nodes, turning on automatic failover. I'm not going to get into it now, but auto failover doesn't function on 2 nodes, and that's to prevent split brain situations. If you plan to use views and indexes, splitting the data paths, the data devices, so that we can make better use of the I/O for those 2 components in parallel, the data itself and the indexes. And then over provisioning when you're first getting started out is going to give you a better experience overall, allowing you to grow into the sizing, both RAM and disk. In some cases, that might mean more nodes to start with and being able to shrink down after you get more experience with the behavior not only of Couchbase, but of your application and Couchbase. And what happens when I start to fill up RAM and start to go a little bit beyond the bounds? Is that okay, or does that indicate I need to have more RAM to cache more data? And being able to learn that under production, under load, without having it cause you any real problems is a big benefit to understanding your own experience. Yes? Yeah, auto failover within the Couchbase software, if it detects one node down, up after 30 seconds, will fail that node over. And going into failover and all of that is a little bit out of the scope of this presentation. We have a bunch of documentation online and some of my own training things recorded. So if you want to talk after the line, I can go into much more detail about how that works. On the client side, when you're getting ready, when you're setting up, and as you're running in production, trying to stay up to date with the latest client libraries. We try to release a new maintenance release of every library once a month, and in many cases there are little bugs that you may not have run into that are fixed. It's going to be helpful to stay up to date with them. All of the libraries are backwards compatible with all of the server versions after 1.8 or so. Make sure that you're always doing the best you can to use one client object per one object per server, per application server, per JVM, per .NET process. It's easy to do this wrong, and that's going to impact your performance a bit. The object itself is what's maintaining the state of the cluster, and so that operation of getting the state, it can be fairly or relatively intensive. So you want to do that once and then reuse that object as much as possible across as many threads. Java, .NET are all thread safe, and we provide recommendations for using them as a singleton. This is a little harder to do in PHP C-based environments, and there are some strategies around that. But what you don't want to do is get into the mindset of creating a new client object for every operation and then destroying it afterwards. So however your application is architected, and talking to your developers, if you guys are the administrators, about trying to reduce that churn of objects as much as possible. Bryce? You have a bit of control from the object's perspective. I would say you don't need to control it in most cases. What you do want to do is just have as few objects as possible and reuse them from multiple threads. .NET is really one of the only libraries that will create more than one connection per node. The rest of them try to do just one connection per object per node against a cluster. Using 2 to 3 server IP addresses or URIs in your client. Technically, you only need one to do the bootstrapping and connect to, but if that one is unavailable, then we don't have any way to connect to the cluster. So providing 2 or 3, even in a cluster of 10 or 20 nodes. We've got some plans in the relative midterm to improve the client itself to automatically detect and do that dynamically, but for today, you need to supply 2 or 3 IP addresses to the cluster. And then turning on logging. Java and .NET have more extensive logging than the other ones, but always have some degree of logging running, something that you can turn on in production without having to reconfigure, recompile, is useful when things do start to go wonky. And if you're not already using Moxie, don't use Moxie. That was for our legacy applications before we had client libraries. So if you are using Java, .NET, PHP, Perl, Python, Ruby, Node.js, or C, use our client library. And if you do have to use Moxie, and if you don't know what I'm talking about, great, and we'll ignore that. But if you do need to use Moxie, put it on the client side and not talk to it on the server side. Okay, so let's talk a little bit about the maintenance and management that goes on. So Couchbase does a lot of work itself, does a lot of health maintenance itself, and especially around the cache management, disk compaction, and index updates. Occasionally we want to tune one or more of the above, but it's more about monitoring that they are operating successfully. So for cache management, we have that built in, very tightly managed caching layer, and that is going to handle everything from removing data from RAM after it's been persisted to disk, as well as bringing it back up from RAM, back up from disk as you make requests for it. In most cases, you're just monitoring this and making sure that the majority of your requests are being served out of RAM. In some cases, there may be situations where you want to tune the amount of RAM that, or the thresholds that are used there. Views and indexes, we're also keeping up to date ourselves. We, by default, do it every 5 seconds or every 5,000 changes. We will trigger a view update. Also, almost every client access is going to trigger or perform a view, an index update. And so, again, all of this should be done automatically without you having to worry about it. If you're seeing some problem there or some slowdown or some delay, there are things you can tune to speed it up and to make it happen more frequently. Disk compaction is a particularly interesting feature that was added in 2.0. It's usually one of the things that just happens in the background, but it's something to be very aware of because the failure of it to function can result in running out of disk space. I'm missing one slide in here, but because of our append-only file format, actually let me skip ahead. Our append-only file format on disk, every write we make is a new record to disk. So every update, every delete, every insert. And so if we imagine an example layout of adding one document, adding another document, adding a third document, all sequentially along in the disk file, as you continue writing and continue updating, Now when we update document A, the old one still remains taking up space on disk. We've done things to update and make sure that you're only accessing the latest one, but the ability to write sequentially to a file is actually a big benefit for us, both in resiliency, redundancy, and also performance. But as you continue writing, you'll see that there become these holes or this wasted space on disk. And it doesn't really impact performance so much as just using up space on disk. So periodically, the software will detect the percentage of wasted space and automatically come by and clean it up. And what it does is identify, okay, there's 30% or so of data wasted here. I'm going to rewrite the file with only the latest copy, delete the old one, and allow things to keep happening. So let me go back now to that other slide that should have been there. This all happens automatically, happens in the background. It uses some disk I/O and CPU, but if the majority of your access, the vast majority of your requests are coming into or out of RAM, you're not going to see any performance impact of this going on. And we allow you to set the threshold at which it kicks in. By default, it's 30%. For very update-intensive applications, we've seen 60% or higher be a good adjustment to make. This can be adjusted online without having to restart or reconfigure anything. You can control the time of day that it happens in or out of. So if your application reads more heavily from disk or you rely more on the disk I/O, you can configure compaction to only happen outside of peak times. Keep in mind that means during those peak times, your disk space is going to grow more and more, which means you're going to want to have more disk space to hold that. The settings are per bucket or global, so there's one global setting by default, and then you can override it on a per bucket basis. It operates on both the data files and the index files. So let me skip through this now. The tuning of this is a space, time, and I/O trade-off. If you have infinite space, there would be no need to ever do a compaction. If you had infinite time to do it, you would be able to do compaction all the time. If you had infinite I/O, you could do it all the time. And so it's the trade-off of what am I doing at the disk, how much space on disk do I have, what is my workload pattern, be it just inserts or lots of updates. And so leaving the default of 30% is fine. 60% we've found better for write-heavy or really update-heavy workloads. And this is because with update-heavy workloads, your fragmentation is actually going to grow faster, but you want to wait until it gets to a certain level before doing one big compaction that's going to have more of a benefit than doing lots of little compactions if it's constantly growing and constantly changing. Correct. So just to repeat, your reads and writes into and out of memory are not impacted at all by the compaction going on underneath. If your read pattern is such that you are reading more from disk because you have more data than you have RAM available, all of that is going to contend for the disk I/O. And so the more work you're doing at the disk, the more impact that's going to have. But the less and less you have of that, the less and less impact compaction will have, to the extent of having none if it's not. If you're doing it mostly out of RAM. One other point on compaction, it's incremental. We do it on a shard by shard basis. And so there's 1,024 shards in the whole cluster per bucket. That's distributed across all of the nodes. All of the nodes are doing this compaction incrementally on their each individual shards. And so while we may not ever be able to go from start to finish through the whole data set, a all or nothing compaction, we're doing it in slices of 1,024 at a time. All the nodes are doing it in parallel, so you actually get an incremental compaction of the overall data set. Okay, so some of the more manual administrator things that you're going to be tasked with, scaling, upgrading, dealing with failures, and backup and restore, and we'll go through these. The biggest part of this is going to circle around monitoring, which we have another session for that I don't want to get too deep into all of the different statistics, but Anil later on today will go through that in much more detail. So everything about scaling with Couchbase, is linear. So needing more RAM, you get by adding more nodes. Needing more disk, you get by adding more nodes. And monitoring the sizing parameters, monitoring the factors that indicate this is what's going to drive you to deciding to add more nodes. Your first instinct should be to add more nodes to distribute the workload, distribute the data more across the cluster before you start thinking about scaling vertically and making those nodes more and more powerful. That certainly is something that you can do and that you may want to do as your cluster grows and grows, but taking a 3-node cluster and constantly increasing the RAM in each one of those nodes is going to give you less of a benefit than adding a 4th or a 5th node. So these are some of the introduction of some very high-level statistics that make the most sense to monitor. Like I said, Anil's presentation later on today will go into much more depth. But you want to have an idea of what your application is doing. What are the operations per second, the reads, writes, deletes, how much expiration is going on, and have an idea of what the latency back to your application is. Couchbase should be responding in less than 1 millisecond on a gigabit Ethernet network, up to about 2 milliseconds in Amazon. If your network is adding more and more latency, that's going to increase the latency back to your client. If you're expecting sub-millisecond latency and you're actually getting 2 or 3 or more, there's something wrong, and that's something you want to be aware of and resolving. So having an idea of what your expectation is and making sure that your application matches that is part of the ongoing monitoring of the entire system. And then looking at RAM, looking at how many requests are being served from disk as opposed to from RAM, looking at how much percentage of your data is cached in RAM versus on disk. All of these things will give you an idea of the expected behavior and performance of your cluster, and those are the things that are going to change as you add more data or add more workload. And then at the disk level, we typically use the disk write queue as a good proxy for available disk I/O. There's lots of other things that are operating on the disk: compaction, rebalancing, taking backups, doing views, and cross data center replication. But the easiest way to look and see whether you have enough disk I/O, and the first thing that will suffer when you don't, is that disk write queue. Is your application writing into RAM and having that written down to disk? If that is constantly low enough, and low enough depends on your application, then everything else you're doing is also sized correctly. Jumping ahead to this slide, if you look, this is an example of one of our customers on an older version of the software, but you see the disk write queue going up and going down, going up and going down over the course of a day. There's a spike there. It's probably a Saturday night, but it comes back down to 0 at the end of the day. And this is an indication of a well-sized cluster. This is an indication of Couchbase's caching layer doing the right thing by buffering those writes, not impacting the performance of each one of them, but also at the end of the day, as the workload goes back down, being able to eventually persist all that data to disk. If we were to see the peaks constantly getting higher and higher, if we were to see the valleys constantly getting higher and higher, that's an indication that you're running out of disk I/O, because over time we're not able to get all of the data down to disk. Question? No, so the question was, is the data persisted for every update? Anything in RAM being changed in RAM before it's written to disk is only is deduplicated in RAM. And so when it comes down to the bottom of the disk write queue, whatever its current state is, that's what's persisted to disk. But it may have changed a few thousand times before it gets there. So we don't have to persist every single update. And then that's actually a benefit in many cases for applications that are writing the same object multiple times over the course of whatever the period is. That's true. Anything in the disk write queue that's not been persisted to disk, if the machine fails, is not available anymore. But that's why we have off-node replication that goes RAM to RAM without any interaction with the disk write queue, giving you that high availability between nodes, so that if a node goes down, you should be able to fail over where the data is now kept up to date. In the replication queue, it doesn't sit there at all. As long as it takes to write it down. We are writing as fast as possible and as fast as the disk allows us to. There's nothing in Couchbase that's saying I'm going to wait, or nothing for you to trigger to do a flush to disk. No, we're constantly writing as fast as possible. It's just that the data is coming into RAM faster than we're writing to disk as that queue is growing, and the workload is, you can see the creates or the sets per second, the writes per second here are also going up and down. So at this level, that's faster than our disk is writing. That's why the queue is going up. But the workload comes back down again at night or at the end of the day, and that's when our disk queue is able to catch up. If it never catches up, then you are in a situation where you need more disk I/O. And that's where you would see the queue going higher and higher. We're not coming back down again. Of the disk persistence, yeah. Okay, let me get through some of these quickly. We have about 10 more minutes. Just as another example of the scalability, this is a benchmark that we published with Cisco and SolarFlare a few months ago, showing a single node handling about 260,000 operations per second. This was a mixed read-write workload, but again, all into and out of RAM. Adding a second node, a third, a fourth, and a fifth allowed us to get up to about 1.6 million operations per second across the cluster. Let me hold questions till the end. The other things, moving on for maintenance, for upgrading the cluster should be a very, very simple exercise. Adding nodes of a new version, removing the nodes of the old version, that can be done simultaneously with a swap, will allow you to upgrade from one version to the next. Couchbase is compatible with 1.8 all the way up into 2.0, so you can do this rolling or online rebalance or online upgrade without any downtime, and then and not have to take the system down. This is also our general approach for any sort of planned maintenance. If you have to do a hardware refresh or patching the kernel or migrating into a new set of servers, our rebalance should be able to do all of that online without you having to take the system down. If you have planned maintenance that you need to do, removing and rebalancing the node and or swapping it with a new one is going to ensure that the data is replicated throughout the entire process, and make sure that those replicas are kept up to date so that if there is a failure at any point, you have a full copy of the data. On the other side, when failures do happen, Couchbase makes it very easy to manage that. In some cases, we'll do it automatically with our failover, or you can manually failover. And we can talk later about how that automatic failover works, but anything can trigger it externally as well. The thing to note is that this does not recreate replicas. We don't want to add more data, more load on a cluster that has just suffered a failure, which might push it further into failure. And so the failover event itself is just to activate the data so that your application can continue accessing it. Afterwards, you're going to want to return the cluster to capacity, do a rebalance, which is going to lay the data out again and recreate the replicas. So if we take a look at the application servers accessing server 3, for an example, in reality, they're accessing all of them all at the same time. When server 3 goes down, there's going to have to be some operations that fail. There are some operations that were already sent out to the wire that need to time out. There's some degree of time between when the failure is detected. This goes to Couchbase being a CP system versus an AP system. We can talk about that later. But once the failure is detected, a failover takes place, whether you triggered it or whether it was triggered automatically, and that activates the replica documents elsewhere in the cluster. They've already been replicated there. All this is doing is turning them on, telling the application that there's a new location for those shards, for those documents, and everything continues. After this point, you would either bring this server back online or add a new one, do a rebalance to get a full replica set. If this node rejoins the cluster after it's been failed over, its data is considered invalid. At no point will we introduce stale data back into the cluster. Okay, just a couple more points. Backup is a very easy process. We have a script called CB backup, takes the data out of a cluster, writes it down to a file. This is an online operation, should not impact performance. 2.0 has made this much better than 1.8 was. The one thing to be clear about with this, it's not a point-in-time snapshot. We're not yet able to provide a consistent cross-node distributed backup, but the backup is valid. The data there will be will be guaranteed to be usable, and it's done online, so you don't have to take the application down. Restore is really just a matter of going the other way. We have a script, CB restore, that reads off of the backup files and pumps that data back into a cluster. This allows you to restore data into a cluster of any size, any different configuration, different name, different location, without having to match the original one to the new one. Okay, I went through a lot of that quickly. These slides will be made available online. If you want more, we have a lot of documentation. I've written a few blogs and write-ups on these different considerations. I invite you to read them. And I've got about 5 more minutes for questions. I wanted to make sure we left some time.